And let's come to the slides again. So it's 10:26. We have some time, no? So yeah, so let's get back. So whatever, so two questions we discussed fully, other questions you think about it later. By the way, number 3 is one of my favorite questions. Huh? So I will give you just one hint. I think the easiest way is if you assume Picard's theorem. Anyway, you know the statement of Picard's theorem, though we are going to see the proof only much later. So if you assume the Picard's theorem, then there's a very nice proof. Okay, so let's get back. So we have seen how well behaved power series representations are. Functions representable by power series are extremely well behaved. What do I mean by extremely well behaved? You can differentiate as many times as you want. So therefore, it's very natural to ask how to produce functions which are representable by power series, right? Because once you can represent, if a function is representable by power series, it's extremely well behaved. Therefore, we are interested in finding out which functions can be represented, how to get such functions, functions which are representable by power series, natural question. So that's what we will look at. So here is the basic idea. It's a very nice thing. So the basic idea is, suppose you can think of something like this. So it is an integral. This is what is called a path integral. You would have seen these kind of integrals in 412. So suppose you have d zeta by zeta minus z over some gamma. Suppose some such thing is there. Of course, we have to make sense of this. So first of all, recall what is a path integral. So we want to say that such a thing is always representable by power series. This is what we are going to do. But let's just say, so what is gamma? Gamma is a path in C. What is the meaning of that? That means it's a curve. It has its parametrizing interval, which is a closed interval, AB in real line, and it's valued in C, and that is what is called a curve. And a curve is called a path if the function gamma is piecewise continuously differentiable. Right? And what does that mean? Piecewise continuously differentiable. You can subdivide, you can partition your interval so that to a finitely many subintervals, and in each subinterval, the function is differentiable and derivative is continuous. Right? So continuously differentiable piecewise. Then you call it a path, and once you have a path, and if you have any function f on the range of the path, so gamma of AB, Rudin's notation as gamma star, we will follow Rudin. So if you take gamma star, which is just gamma of AB, the range of AB, and if you take any continuous function on the range, then by definition, this is the definition of the integral over gamma fz dz. By definition, this is f of gamma t, gamma prime t dt, where dt is the usual Lebesgue measure on the interval AB. If you, there may be two students who haven't done measure theory, doesn't matter, it's your Riemann integral. Because we are assuming continuous, etc., it's Riemann integrable, and whatever is Lebesgue measure, which you will do a bit later, maybe the Lebesgue integral coincides with the Riemann integral. Okay, so this was your definition. You must have done all these things, I'm sure. Okay, so by definition, integral f z dz, we mean integral a to b f of gamma t, gamma prime t dt. It's just one variable integration on the closed interval ab. Okay. So
when
now,
we mean
yeah.
here when we mean gamma t, here when we mean gamma t, we have the differentiation with respect to the real variable, right? That just
yes,
t.
the variable is t. T is from the interval ab. So
So gamma
prime,
is u plus iv, then it's u dash plus iv dash.
absolutely. Gamma prime is u prime plus iv prime. So that's a complex number, right? For a given t, that's a complex number. F of gamma t is also a complex number. It is multiplication of complex numbers. In multivariable calculus, you would have had a modulus or something because everything you wanted real. Here we don't care. This multiplication of complex numbers, and then you just integrate. Yeah. So everything is u plus iv. So it will be u dt plus iv dt. Good that you asked. Okay. That's fine, no, Ariman?
Yes, it is.
Yeah. So let's go to the next slide. Therefore, This makes sense. Now you know this. Now I can define a function, right? I can define a function using this variable z. I can treat this as, so I'm integrating with respect to zeta, so that goes away. That's no longer a variable, but there is this variable that I'm introducing z. So this in this integral was just a number z. Now as that number varies, I get a variable. So I have f of z, I can define like that. And where does this make sense? This makes sense whenever z minus zeta minus z is non-zero. So this makes sense whenever, so where is zeta from? Zeta is from gamma star, right? So whenever z is outside gamma star, if you take z any complex number which is outside gamma star, this integral makes sense because 1 by zeta minus z is a continuous function. It's a very good function. It's a continuous function whenever this is non-zero, and that is guaranteed by taking your region of consideration to be C minus gamma star. Okay, depending on gamma star, it may not be a region maybe, but anyway, it's an open set, and this makes sense. Okay, so I'm defining f on omega, which is a complement of gamma star, and this function you can consider. And now, you know, some nice manipulations we will do. So we are going to say, our assertion is that this function that we have defined is representable by power series. Meaning, if we are taking an open disk inside omega, associated to that open disk, I need to produce a power series which converges to f of z at every z inside that open disk. I need to manufacture a power series, and how are we going to do that? Let's see. So what you know about power series? See, theoretically we know something about power series, but concretely, what is one power series that you knew from your school days? It is a geometric series. In fact, this is the only power series that one knew at some point, right? So 1 by 1 minus w is summation w power n. And does this make sense always? No, there was a condition, right? In order to get convergence, what is the condition? Mod w should be strictly less than 1. Once you have this, so there is at least one power series you have seen from school days and you are very, very comfortable with. And whatever else we need to conclude about power series, we are going to shift the question to this geometric series and then conclude. That is the basic idea. Okay. So keep in mind the geometric series and we will make use of this. So consider it this, right? We want to say that the function f of z is representable by power series, and recall the definition. Representable meaning given any disk. You give me a disk and I will produce a power series which converges on that disk to the function. So you have given me a disk now. So consider DAR contained in omega. So what does that mean? If you take DAR, the disk DAR contained in omega, and if you take a number zeta on gamma, meaning in the range of gamma star, try to visualize. So you have some curve gamma and you are taking a point zeta on gamma, and omega is the complement of gamma star, and you are taking a disk there, DAR. So if you take a zeta in gamma, zeta is much farther from A than R. No, R is the boundary, right? So R is the circle of the boundary circle of the disk. This is an open disk. It is a boundary, and the distance between A and the boundary is R, and zeta is farther. So because omega is the complement of gamma star, you can see that mod zeta minus A is bigger than or equal to R for zeta in gamma star. Clear? Therefore, if you take any z in the open disk, you can consider mod z minus a by mod zeta minus a, and you have observed that mod zeta minus a is bigger than r. Therefore, this is 1 by zeta minus a, that is less than or equal to 1 by r. Therefore, this is less than or equal to mod z minus a by r. R is a positive number, right? So mod r is r, and this is, what can you say about this? This is strictly less than 1. Why? Because z is from DAR. DAR is an open disk. Mod z minus a is strictly less than r is this open disk. Therefore, mod z minus a by r is strictly less than 1. All of you are with me? It's just a observation that if you consider this quantity, it is strictly less than 1. Compare with, our recalling something from our school days. You know the geometric series. Whenever something has modulus less than 1, 1 by 1 minus, that thing has a nice geometric series, power series expansion. And here you have something whose modulus is strictly less than 1. This reminds you of, this W. Okay, so you've got a nice candidate for W, and we can plug into the geometric series and just observe what we are going to get, just curiosity. Okay, so you can take this to be W and try to do this computation. So you have got a candidate for W. Now observe what is 1 minus W if W is that quantity, Z minus A by zeta minus A. So it is 1 by 1 minus Z minus A by zeta minus A. Cross multiply and write that. So it will be 1 by 1 minus Z minus A by zeta minus A. So zeta minus A minus Z minus A. That is zeta minus Z by Z minus A. So by zeta minus A comes to the numerator. So it is zeta minus A by zeta minus Z. Right? This is what you are getting. And therefore, what is 1 by zeta minus Z? I am interested in 1 by zeta minus Z because that's what is coming in my formula. Right? The integral was integral of 1 by zeta minus Z. So 1 by zeta minus Z is a quantity that I am interested in. And here you get 1 by zeta minus Z is, and this has a geometric series expansion because this quantity by our choices is modulus is less than 1. So this will be summation modulus of summation Z minus A by zeta minus A whole power n. Z minus A by zeta minus A whole power n, and there is this zeta minus A here which has come down. So this has become n plus 1. Agree? 1 by zeta minus Z is 1 by zeta minus A times this, and this would have been Z minus A by zeta minus A whole power n, and by 1 by zeta minus A. So this zeta minus A whole power n has become n plus 1, and this thing is n. So you've got a nice series expansion for the quantity 1 by zeta minus Z. Now we were interested in Fz, which is just the integral of 1 by zeta minus Z. So you integrate on the right hand side. And when you integrate on the right hand side, you will get integral of summation this thing. And I'm going to say that is sum of the integrals. Integral of the sum is sum of the integrals. Assume you can do that. If you can do that, then you have got sum of integral of this quantity with respect to d zeta. And then what you're getting is Z minus A power n, right? There is no zeta there, so that comes out, Z minus A power n. And what is Cn? Cn is integral d zeta by zeta minus A power n plus n. You agree? Assume you can interchange integral and summation, and then this is what you're getting. Summation of integral d zeta by zeta minus A power n plus 1 times Z minus A power n, which is without zeta, so that has come out. So Cn is this thing. This integral will be some constant, and that is a coefficient Cn. So you have got f, you have got the power series expansion for f on that disk, and you have proved that f is representable by power series. Okay, so one thing that we have used is integral of the sum is indeed the sum of the integrals. Where we have we used this thing? Because here when I'm integrating, the integral is coming here, and then I'm taking the integral here. So I'm changing the sum and the integral, and this is okay because we are on a disk where the power series is absolutely and uniformly convergent. Right? Radius of convergence, if you remember the definition, is such a thing such that inside the convergence is the best convergence. It's absolute and uniform. And once you have uniform convergence, you know that limit and integration can be interchanged. So integration and limit interchanging is okay. So we have answered that why. And one more question you can ask, you have got this, but why is this a convergent power series? Right? You have got a power series, but why is this a convergent power series? There's no root test, nothing, because I mean we haven't taken the limit of lim sup of mod Cn power 1 by n. You could have done that, but we haven't done that either. But even without that, we know this is convergent, no problem, because by the proof, the way we have constructed this, you are showing this equality, fz equal to this. And the left hand side is, the function taking a value, so this is some finite number, f is a function. So f is taking some finite number, finite value, and it is that value by our very construction. So convergence is not an issue. So what we have shown.
Could you repeat the statement again?
The last statement. The
Yes,
last
sir.
statement about convergence, sir. See, what I'm saying is we haven't really bothered about the convergence of this by root test or something like that, because by our proof, the way we have proved this, we are showing the equality fz equal to this series. So forget about this series, come to this part. We have shown the equality, it is fz. But what is fz? Z is one thing from your domain and f of z is its value. So that is some finite complex number, right? Therefore, this series at that point z is that number. So convergence is done.
Yeah.
Is that
Okay.
okay, Ariman?
Yes, sir.
Yeah. So, and then, Rudin, if you look at the book, I did not copy it on the slides because I was interested only in one argument. Rudin has a further note which says that from this, we've also got the coefficients from the proof. You can take mod Cn and you can bound it, right? Modulus of the integral is less than or equal to integral of the modulus. You can bound it and you will get something, and then you can apply root test and you can show the convergence like that also. But I'm not unduly bothered about that because we have already shown, because you have got a finite quantity on the left. Okay. So I formulated it in a very simple situation, but the same idea, exactly the same thing will go through and will give you a very general result. The proof is the same, but the statement can be much more general. And this is theorem 10.7 in Rudin. You can look at the book later. The only reason I formulated the very minimal thing is that because I assumed maybe Chirag and Agreement did not have a measure theory course yet. I think the MSc students already had a measure theory course, but you don't need to worry too much. I will just introduce the words and you can take it as your measure theory course. Okay. The point is, the only thing that you need to know right now, you will learn it rigorously when you take the measure theory course. I think it's a compulsory course for you. Is that just like Riemann integral or Lebesgue integral that you do on an interval or on the real line, abstractly you can integrate things. So what you need is a space called the measurable space, and mu is what is called a measure, which means given a subset which is nice, quote unquote measurable, then associated to it you can have a value. So for an interval it's its length. If you are in the plane, it's the area. If you are in three-dimensional space, it's the volume. In multivariable calculus, you have already seen this, the n volume, right? Jacobian and all those computations. So measure is the abstraction of that. So wherever you can make sense of volume, so you abstractize. You will have some axioms and properties, and you have the notion of a measure space. And this measure, the volume can take complex values also. That's again part of the abstraction. So if you have a complex measurable space, that basically means you have an abstract space X where you can integrate with respect to this measure mu, and you will get a finite complex number. And then you can take a function which is measurable, which means you can integrate with respect to mu, and the integral will be finite. So suppose you have a function like that, and suppose you take a region domain in C which does not meet the image of phi. So phi of x will be inside C, and omega is a domain in C which is outside phi of x. The intersection is empty. If you have this much, now if you recall, this is exactly what we had. We will come back to that, but let me just state the general formulation. If you have this much, then you take the function, complex function defined by f of z equal to, as I told you, x is an abstract measure space, therefore you can integrate with respect to the measure. So mu is the measure and integration is denoted by d mu. So if you integrate d mu zeta by phi of zeta, right? Zeta is in x, phi of zeta will be in C. Phi of zeta minus z is not 0 because omega intersection phi x is empty. Therefore, 1 by phi of zeta minus z is a nice measurable function because phi is a measurable function. And therefore, 1 by phi of zeta minus z you can integrate with respect to that measure on the space x abstractly, and you will get a complex function. So this is representable by power series in omega. Okay, so associated to an abstract measure space, you can construct a function representable by power series in omega. So what did we do? We have proved what we have done is we did the case where x is the closed interval AB. This was the parameterizing interval for our curve gamma, for our path gamma. And what was my phi? My phi was gamma. So gamma is a function from interval AB to C. And what was my measure? My measure is the usual integration dt, right? Well, not quite dt, because if you remember, integral dz means what? Integral dz means gamma prime t dt. So my measure is gamma prime t dt. It is your usual Lebesgue measure, usual Riemann integral that you do dt is your integrating thing dt, but just shifted by gamma prime t. That's my new measure. So this was the situation which we have done. But in our proof, we never use the fact that this is our situation. So the general formulation, also the proof is exactly the same. It is just the manipulation using geometric series. Exactly the same proof works, and you have the more general result. And whenever you can state this result abstractly, that's better, because again and again when such a situation comes, you don't have to reprove things. You can appeal, you can take various x, various functions, various measures on various x's, and you will get beautiful results. You will get many functions are representable by power series. And this is very useful for us, because once it is representable by power series, then you can differentiate as many times as you want. Term by term differentiation we have rigorously proved is fine. It works. Therefore, we are in a very happy situation using a simple integrating idea and going to geometric series from our school days. We have a way of producing, manufacturing functions representable by power series in a very abstract set. So I have stated the general theorem. Okay. You might recall from MA521 that you have this slogan, right? Complex analysis is full of nice slogans, right? For example, Liouville's theorem. What is Liouville's theorem? Bounded entire is constant. What a beautiful theorem. You don't need a single math symbol. It's just plain English, one line. You can. It's almost like a slogan, or a dictum, or a proverb, or a line from a famous poem, right? So someone is trying to say something. Okay. So this thing that you have this what I call ODAD, once differentiable is always differentiable. The meaning is not differentiable holomorphic, right? You need differentiable throughout, then it is differentiable throughout. The meaning is that holomorphic functions are infinitely differentiable. This is what I was saying before our break, that we are showing that a power series is infinitely many times differentiable. We showed that the power series is holomorphic, and I said the converse is also true. Holomorphic is representable by power series. And what was the main idea? This is what we discussed now. The main idea, the proof has two main ideas, and the one is this general way of manufacturing functions representable by power series. So how does one prove this? We will come to it again later, but the quick idea: once differentiable, always differentiable. So we want to say that. So what are the functions we know are infinitely many times differentiable? We don't know so many such things. The only thing that we know infinitely many times differentiable is power series representations. A function representable by power series is infinitely many times differentiable. Therefore, one natural idea would be, in order to show that holomorphic functions are infinitely differentiable, show that holomorphic functions are representable by power series, then they are infinitely differentiable. So try to show that holomorphic functions are representable by power series. So how to do this? So now we know a method by which we can manufacture functions representable by power series. How do we do that? By suitably integrating. Right? If you suitably integrate, then you are getting a power series representation. That's by suitably integrating. If you construct a function, we just saw that that function is representable by power series. So the key remaining ingredient is CIF. What is CIF? Can someone tell me quickly what is CIF? What is the full form?
Cauchy integral formula.
Correct, Cauchy integral formula. So Cauchy integral formula tells you with some hypothesis that fz has this integral form. And you look at this integral, this is very similar to what we have done, right? What we have done is f of z equal to integral gamma d zeta by zeta minus z is representable by power series. But the same proof I stated more generally with an arbitrary x, Therefore, instead of the, you can take the same x closed interval AB, you can take the same phi gamma, and the measure I will change a little bit. Instead of gamma prime t dt, if I take the new measure f of gamma t gamma prime t dt, then the general result applies, and then you show that this is also representable by power series. This is just a constant. Therefore, this f is representable by power series by the result that we just proved. So two ingredients. One is Cauchy integral formula, which gives you this integral representation. And second, what we have already observed, if you have an integral representation like this, then it is representable by power series. So take x equal to 0 to 2 pi, because it's a circle, no? Cauchy integral formula, this gamma is a circle, right? On a circle, we would do this. So the parameterizing, good parameterizing is 0 to 2 pi. And phi is gamma, where gamma is cos theta sin theta, that curve, circle, unit circle. And the measured d mu t is f of gamma t gamma prime t dt. Integration is with respect to this measure. And then you can apply the general theorem, and you know that this function is representable by power series. And therefore, it is representable by power series. Therefore, you can differentiate term by term. Therefore, it's infinitely many times differentiable. And you know the coefficient of the power series. Coefficient of the power series is the kth derivative plugged in at a by k factorial, and the kth coefficient at a. Yeah, the kth derivative plugged in at a by k factorial, and the kth derivative of a also you can find. Cauchy integral formula has this generalization where the kth derivative also have a nice formula. If you have derivative k here, so the zeroth derivative had this thing coming to the power 1. So first derivative, this will come to the power 2. Kth derivative, this will come to the power k plus 1. So you even know the coefficients precisely. And so this is a very beautiful part of complex analysis, one variable complex analysis. So you get your general result here. So remark. Yeah, but this is, on this basic thing is on a path only, right? Though this measure was slightly different, these are, very Riemann integral kind of thing. So the remark is, when we do Runge's theorem later, of course it has a more elementary proof in Conway's book, but we are going to follow Rudin, and when Rudin does Runge's theorem, this general abstract measure theoretic space, the observation that we have shown, he's going to use it with a very abstract space X, not some interval in R or something. And we are going to use this result that on an abstract space you can integrate like this, and you can get a function representable by power series. This is going to be very beautifully used in his proof of Runge's theorem. We will come to it much later. I just wanted to give a make a pointer to it right now. And it will also use some results from functional analysis. So I think Chirag and others are MSc students are learning functional analysis parallelly. So by the time we reach there, they would have seen the functional analysis that we need to know. Chirag and Aryaman most likely will not know the functional analysis, but not much. Whatever we assume, we will do. So don't worry. But I would prefer Rudin's proof, so we will do it. Because this theorem also we can very nicely use. So I think it's time, and we will stop here. Any quick questions?
Like, will these PowerPoints be made available somewhere? Like,
yes, Moodle. PowerPoints I'll put on Moodle, and video will be there in our Microsoft Teams as well as on YouTube.
Okay, sir.
So PowerPoint, when I put, should I remove all these pauses? It's up to you. Should I remove?
No, let them be there.
Let them be there?
Yeah.
Okay, then I will leave it there. The only thing is, if you are planning to take a printout, then this will create a nuisance. But if you're not planning to take a printout, then this is better.
Yeah.
Okay, let them be there. I'll leave it as it is. Okay. Okay, good. Any other quick question? Okay, so good. How many participants were there today? 14. So I think 4 or 5 people were absent. Hopefully they will also join next time. As I said in the first lecture, please do come for the live session. I understand internet issues are there, so maybe you can't follow fully, but be around. Let's see. Okay. Okay, so I'll stop the recording and we will meet now next Wednesday, right? So Wednesday 9:30 we will continue. Yeah. If you have any questions, etc., WhatsApp or email or comment on Moodle. Okay. So okay. See you next week.